Welcome listeners again to our next topic of discussion, that is optical mineralogy, and it is in the series of our discussion on fundamentals of geology. And just after our discussion on the physical properties exhibited by minerals on hand specimen, now we will be looking at a few properties that are essential to recognize specifically the rock forming minerals under microscope. So obviously whenever we are talking about optical mineralogy, so it is based on the principles of how a mineral will behave under light. So for that obviously we need to have a thin section or a slide of a mineral that can be viewed under the microscope, or a rock even which is composed of several other rock forming minerals, and then we can view that under the microscope. So obviously for optical mineralogy, like for observing the physical properties of a mineral, you need to have a sample taken from field or from some outcrop. You need to have a physical sample of the mineral to look into the physical properties. Similarly, in case of optical mineralogy, we need a sample of a rock or even a mineral sometimes, and then what we'll do, we'll simply make a thin section out of it. We'll be looking at that as well, and then we'll observe it under the microscope. And after that, it is simply a play of your light rays, that how it is passing through the mineral and how it is behaving, and depending on that, the mineral will show a certain type of color, or even it can show a variation in color, and also some other properties that can be observed under a petrological microscope. So obviously why we are calling it a petrological microscope, because it is different from that of a biological one. In case of a biological one, we don't have an upper analyzer, or there are two polarizer. In case of your petrological microscope, one is actually set at the bottom of the stage through which the light will first pass through, and the light will become polarized in nature, then it will pass through the mineral, and again the same light after getting refracted within the mineral slide or a slide of a rock, it will get double refracted, and then the light will pass through the upper polarizer, which is set in a reverse orientation, or in a orientation orthogonal to that or perpendicular to that of the lower polarizer. So you have another polarizer at the top, which is generally referred to as the analyzer. So if your lower polarizer through which your light is first coming through is oriented, for example, in the direction of east west, then the next one will be, it means the upper polarizer, that is also referred to as the analyzer, will be placed in a manner that is north south. So you have a 90-degree or orthogonal relationship between the lower polarizer and the upper polarizer, which is also referred to as your analyzer. And also you have other, you can say, parts or of your petrological microscope. For example, there is a stage like this with 360-degree graduation like this, and that is also referred to as a stage goniometer, through which you can measure different optical properties. Then you also have this objective lens, and depending on the scale of analysis, you can change the lens from, for example, 1x to even 40x for a normal petrological microscope. Generally 1x are not given in your petrological microscope, neither 40x, but for a standard one there should be a range of 1x, and obviously you have an ocular lens which is also giving you a 10x lens on the top. So it is just a multiplication of the objective and the ocular lens, the scale you are looking at. So if you have 10x already here, you have 1x here, then obviously you are looking at a scale of 10x. If it is more, in that case you can apply a 2x objective here, or 4x objective here, 5x or 10x objective here, and depending on that it will increase. For a 10x here and 10x at the ocular lens, you can get a magnification of 100x. So based on this, you can also play with the scale of your observation, and there are other you can say properties or parts of an optical petrological microscope that are being used for different analysis, but those on those things we are not dealing at this level. They can be dealt in an advanced level of the understanding of the different aspects of the optical mineralogy subject, but here we will be mainly concentrating on how you're mainly on the rock forming minerals that are showing a particular kind of properties under, or the optical properties under your microscope. So again, if I look at the first step before analyzing any rock or mineral under microscope, we first need to understand how a thin section is prepared. So you can simply take a thin section, means a glass slide, and then you can frost that thin section, or you can polish that glass slide. So on the polished side of the glass, you can now mount a rock or a mineral. So how it is done? Obviously with the help of a rock cutting machine, you can take a chip or a slice of that rock, or even in sometimes if you want to make a thin section of a mineral, you can take a chip of that grain, and then you can also mount it on the glass slide, on the polished side of the glass side. Then it is stick on the glass slide with the help of some adhesives, generally epoxy, and sometimes some other adhesives as well. And then you can mark your glass slide, and then after sticking this mineral, a grain of a mineral or a rock which has multiple minerals in it, or rock forming minerals in it, then you can polish that or grind that thin section after attaching it with the rock slide. Then you will start grinding the other part till it reaches, after this grinding and phases of polishing, still it reaches thickness of 0.03 mm, where from which you can study, or which can be used as your next material for the studying the optical properties of that rock, or even in case of a mineral. So now as again quartz is the most dominant mineral among all rock forming minerals, so generally apart from a few rocks which are devoid of quartz as a mineral, apart from that, whenever quartz is present in any rock, we can check it in a qualitative way as well. Like if I am looking at a quartz with a true thickness of 0.03 millimeter, and if your thickness has been made correctly, in that case your thin section means your quartz grains within the thin section will show you this kind of gray kind of color. These are referred to as interference color. We will be referring to that as well. But if the thickness has not been achieved during this stages of grinding and polishing with several carbonandum powder of several mesh size, starting from 120, 220, 400, 600, 800, 1000 and even 1200, in that case these are the different mesh size of a grinding powder, and later on you can polish it as well with some other. You can polish it with alumina paste, you can polish it with diamond paste, which are little bit costlier. Also you can polish it with chrome oxide. So based on that, you are polishing the thin section to reach a level of or thickness of 0.03 mm, so that the true optical properties of a mineral can be viewed under microscope. So these are the two examples. This figure number 10 and figure number 11 simply shows you that when your quartz or the thin section will achieve that thickness of 0.03 millimeter, it will show you this kind of first order gray, sometimes first order yellow as well, but mostly first order gray to grayish white kind of color. And in case when it has not achieved the required or specified thickness, in that case it may show higher order colors. We will be also referring to the ordering of color in a bit. So this you can see just by looking at the microscope. You can say or can have a qualitative idea that whether that thin section is correctly made or not. So the main characteristic of a thin section is that the standard thickness of any geological thin section to view a mineral or a rock is 0.03 mm. Quartz should show first order interference colors at this particular thickness. Special care should be taken to avoid any buildup of bubbles when you are mounting your mineral or rock on the glass slide. You have to be very careful with this mounting process, so that when you are mounting it with the help of some adhesive or epoxy, in that case your bubbles may develop. So you have to take care with that, otherwise your bubbles will appear in your thin section and it will hinder your observation of your optical properties. And grinding and obviously polishing at the last stage should be done very carefully, so that because the thin section is having a very thin thickness, that is 0.03 millimeter, if you grind it further, there is a possibility that the whole mineral grain or the slice of the rock that you are using to make a thin section is completely grinded and removed from the surface of the glass slide. So in that case you have to be very careful, otherwise your whole process of making a thin section will simply be lost. So to obviously, whenever we are looking at a mineral or a rock, you need to understand that how light behaves under a microscope and how light passes through a mineral and what will happen to that light. So the first thing that is very important to understand is the refractive index of a mineral. Obviously that is property of the light passing through it. So if I start with taking an example of, for example, diamond, then the refractive index of diamond has been determined to be 2.4, because light travels 2.5 times slower in diamond than that of air. So now I can also say that if every mineral has a specific refractive index, then it can also be treated as a diagnostic property of that particular mineral. So in vacuum, light travels at 3 into 10 to the power 8 meter per second, but definitely when there is no vacuum, there is regular air, light will travel at a much slower speed. Therefore, we could compare light's velocity traveling through an unknown mineral, for example, in a thin section, to that the speed of the light or velocity of the light in air. So the refractive index can be expressed as a function of the velocity of light in air divided by the velocity of light in the mineral. So be it a known mineral or be it an unknown mineral, you can determine the refractive index by simply applying this equation. Then certain wavelengths of light are absorbed and reflected by minerals, giving them their colors. So obviously whenever you are looking at a mineral under microscope, you will get to see certain colors in it, and also these colors can change over the rotation of the stage. We were looking at that number 360-degree a stage graduation in the photograph or figure of the petrological microscope. So you can rotate the stage, likewise your slide will also rotate, and then you can also have an idea that how that whether there is any change in the color or there is no change in the color, and that is grouped under a property that is pleochroism. We will be discussing about that. So when passing through a mineral in thin section, light is slowed down, and the amount that is slowed depends on the mineral. So obviously it is the refractive index of the mineral that is controlling the velocity of the light. This retardation of light can be quantified by comparing the relative amount of retardation through unknown substances to that of known substances such as air. Simply, if I look at this equation, then the velocity of light in air by the velocity of light in mineral will give you the refractive index. But if you are looking at a mineral under microscope, you are not being able always to quantify it like we can do with the help of this equation. In that case, we simply use a term that is referred to as relief, that how well your grain boundary or the surface of that mineral is being visible under the microscope under plane polarized light. We will be looking at that what plane polarized light is and what do you mean by cross polarized light. So we will be going into that, but just to mention the property here. So if by the rotation of the stage, if the mineral is displaying only a single color, or for example it is colorless, then that case we will say that this mineral has no variable absorption of light. So that's why it is giving you a standard color. As well as if I can look at the boundary of a mineral, that the boundary is well defined and the surface is uniform, for example, and you can view the surface for other properties like cleavage and fracture also, then we can say that mineral has a high relief, which is a, you can say, which is a function of the refractive index of that mineral. If on the other hand that particular mineral is not that visible, or if the grain boundaries are faint, we will say that mineral has a very low relief, and again it's simply a function of its refractive index. And like I was mentioning about the pleochroism, that if a grain of a mineral with the rotation of the stage is changing color, then you can say there is variable absorption of light through the mineral that is going on. So that's why due to this variable absorption of light, the mineral is exhibiting a different color with a rotation of the stage. So now coming back to our discussion, like when what will happen to light when it is passing through the minerals. So consider light traveling through one material to another, like this figure. So the incident ray is getting refracted or bent when it enters the second the medium. For example, you are transitioning from air to glass, simply like that we do in case of optical or petrological microscope, where your light is coming from the bottom and it enters the glass slide and it gets refracted. Why? Because of the presence of the mineral that is present on the glass slide, or the thin section that you have made. So the angle between the line perpendicular to the boundary and the refracted ray is the angle of reflection. So your Snell's law simply related these angles of incidence, that is I, or can be also referred to as 1, and the angle of refraction, that is the angle of the refracted ray from the normal with respect to the boundary of these two medium. So the Snell's law can be denoted as N1, that is the refractive index of your medium air. For example, here we have taken air and glass. So N1 is the refractive index of air, and multiplied by the sine of the incident angle is equal to again the refractive index of glass multiplied by sine of the angle of refraction. So these angles can be measured directly with a refractometer. Otherwise, if you don't have a refractometer, then we can simply observe the qualitative factor, that is the relief, like just I was mentioning. So if you have a higher relief, and obviously that is a function of the refractive index. So if you have a higher relief of a grain, then it will be visible more clearly, the boundaries will be more clear, the surface will be more clear of that mineral in comparison to a mineral which is having a low relief. So now coming into the other idea, that is a polarization of light. When an unpolarized beam of light is simply coming from the bottom of a microscope, what is happening, that you have a polarizing film that is set earlier. Now polarizing films are used to construct a polarizer. Earlier there is a thing called Nicol prism. It is nothing but crystal of calcite. They are cut and mounted in a rhombic manner. We are not going into the details of preparation of a Nicol prism. You can find literature about that very easily. Simply, if I am now looking at a polarizer, what is the job of a polarizer is to polarize the light which was unpolarized in nature earlier. So what it is doing, if a light ray is coming like this, then from our understanding at school level also, we know that the light vibrates in all direction perpendicular to the direction of the propagation of the light. So you have the propagation of the light in this direction. With respect to that, orthogonally the light is continuously vibrating in all the direction 360 degree. like this, but all are orthogonal to the direction of propagation of the light. So you have this multiple direction of vibration with respect to the propagation of the light. So when it is entering or passing through the polarizer or the polarizing filter or film, what is happening that now after entering through this polarizer, the light will now only propagate in one particular vibration direction. Sorry, it will vibrate in one particular vibration direction, and it will continue to propagate in its own direction. So now the vibration direction will is constrained within a single plane. So now I can say that as the vibration direction is constrained or restricted within a single plane, then I can call this light as plane polarized light. Earlier it was unpolarized light. Now you have polarized the light in a specific plane. So now it is referred to as the plane polarized light. Now if you again can think of two polarizers like we get to see in an optical petrological microscope, in that case if I start again with an unpolarized light coming from this side, for example, so it is coming and entering into the first polarizer, which is kept in an east-west fashion like this, for example. So your light will be polarized like this. Okay, so this now you have the light that is passing through or that is now propagating across the first polarizer will now go with a specific vibration direction in a specific direction. Now again if I put a polarizing film just above that, then what will happen, depending again on the orientation of the polarizing film, if I make it like this, east west or horizontal, then this plane polarized light will also be able to pass through it. But if I make it north south, or if I make the polarizing film vertical, in that case this will get restricted and it will not be able to pass through the upper polarizer, or which we refer to as the analyzer. So if you are looking at a microscope without keeping any slide, simply if I look at the microscope when there is only polarizer, when the light is only passing through the polarizer, you can still see some light when you are looking through the ocular or through the lens. But if I simply insert the analyzer, that is the upper polarizer, if I simply insert that, then you will not be able to see anything. Why? Because it is now also restricting the, or it is, you can say, kind of restricting the plane polarized light even to pass through the upper analyzer, that is the upper polarizer. So if there is no slide that is kept on the microscope stage, in that case you can see some light with the presence of the polarizer, but once you insert the analyzer at an orthogonal relationship with the polarizer, there will be nothing. You will only see dark or black, so you will not being able to see any light. So now what is happening between this? Now you have inserted a slide. So apart from, now you have the polarizer and analyzer that are kept in the microscope. Obviously you can insert it, you can simply take it out, but you also now have a mineral that is present within a thin section that is now kept in the stage. So what is happening now, the property of certain minerals is to split the light again into two rays, which are generally referred to as the ordinary ray and extraordinary ray, and they again have two vibration directions and they are also mutually perpendicular to one another. So it simply occurs in anisotropic minerals, where the speed of light varies depending on its direction through the mineral, and it is quantified by the birefringence index, which measures the difference in refractive indices between these two rays. So now again, whenever your for example polarized light, after coming from the bottom where it is coming as unpolarized light, then it is getting polarized and finally it is entering into the stage where you have the mineral. Then since soon after entering the thin section or the mineral, again it will that plane polarized light will be refracted into two rays, that is ordinary ray and the extraordinary ray. One has a higher velocity, another one has a a relatively lower velocity. But also there is a variation in their vibration direction. For example, again you have two rays now with, for example, east-west vibration direction and north-south vibration direction. So now these two will finally pass through the mineral, and based on that you can say if this kind of double refraction is not happening, in that case you can group it under isotropic material. So again, if I look at that, it is this double refraction commonly observed in crystals, liquid crystal and some biological materials as well. So your application includes polarizing filters, wave plates and optical mineralogy for obviously identifying minerals based on this. So what is happening here, again if I go to this diagram now, you have a relatively faster, for example, ordinary ray or extraordinary ray, and a relatively slower extraordinary ray or the ordinary ray. So now after getting out from this, they are now entering the upper polarizer, which is also referred to as the analyzer. So now what will happen, there will be, because of the relative velocities of the two rays, ordinary and extraordinary ray, there will be some difference in their velocity, as well as there will be difference in their refractive index. So what will happen, that this refractive index can be measured with the help of birefringence, that is your lambda or del n is your birefringence index, and the difference between the refractive index of the extraordinary ray and the ordinary ray is referred to as your birefringence. Then what is happening, when these two rays, two components resulting from this birefringence and that is obviously the property of the mineral or the slide that you are dealing with. So due to that you have now this extraordinary and ordinary ray which are propagating at two different speed. So now after analyzing, it is passing through the analyzer, they have a kind of means you can say they are not in phase, they are now out of phase. So obviously there is some phase difference between this extraordinary and ordinary ray like this, and this phase difference is referred to as your del n, or which is also referred to as the retardation. So your retardation, that is del n, is equal to the thickness of the thin section. So you can see here your thin section is also a function of the birefringence, as well as the birefringence is also a component of this, means determining your retardation. So your retardation is finally getting controlled by the birefringence of the two components, as well as from the thickness of the thin section. If it is thick, then the retardation will be more. If the thin section is of means you can say more thin than the standard thin section thickness, in that case it will have a lesser retardation. So your standard thin section is again essential to analyze or to interpret a specific set of minerals or a rock. So based on this birefringence of different minerals and thickness of the thin section, that is in millimeter, you can, after you put the analyzer, you will be able to see this interference color because of this out of phase interference between the ordinary and the extraordinary ray. Due to this, retardation will happen, and due to this retardation you will be able to look into several colors under your cross polarized light when you have two polarizers that are effective in this. So in that case you can also have a look at this chart where you have this values of birefringence on one side and thickness of thin section in millimeters on other side. So your 0.03, this line remember, is your ideal thickness or standard thickness of a thin section. And these are the different orders of color that you can see, this rainbow like colors that are present, starting from the first order, where you start from this black gray to whitish gray to some yellow, then orangish yellow, and finally a red band that separates the first order and the second order color. Again, you will look into this Viv-gear, violet, indigo, blue, green, yellow, orange, red. Again a red band will come, and then you are transitioning into the third order, and you increase, as you increase this order, you can say it will become more pale in nature. So for ideal thin sections, generally we get to see a color of up to, you can say, very higher order, means very higher third order, or a little bit lower fourth order. So for a standard thickness of 0.03, you won't be able to look at the higher or even pale colors in a microscope. So based on these values of birefringence and the thickness of the thin section, you can look at the difference interference color of particular minerals. So now some before I go into the final part of some properties of the rock forming minerals, there are certain properties. To start with, pleochroism. Certain minerals display different colors when viewed under different angles. This property is called pleochroism, and it is due to the variable absorption of light waves only under the view, when the mineral is being viewed with a polarizer only, without any application of the analyzer or without inserting the upper polarizer. Then the other optical characters include what is possibly one of the important thing, that is whether a mineral is isotropic or not, or it is anisotropic or not. So your isotropic minerals have uniform optical properties in all directions. Your anisotropic minerals vary in optical properties depending on the direction of light and crystal orientation, and this is also related to the crystallographic orientation that we have discussed again the basic idea of crystallography earlier. So it is related to that, as well as it is related to something called optical indicatrix, but we are not discussing that at this basic level of understanding. It requires detailed, you can say detailed lecture solely on optical mineralogy to understand the intricacies of an optical or optical indicatrix. Dispersion refers to the separation of white light into its component color as it passes through a mineral. So minerals with high dispersion exhibit fire scenes as flashes of color. Dispersion is particularly notable in some gemstones like diamond and sphene. Relief that we have discussed already, it is simply a function of the refractive index of the mineral. So a mineral with higher refractive index will have very well defined boundary and surface. Mineral with a very low refractive index will be very hard to recognize because of its faint nature of its grain boundary and very, you can say, faint nature of its surface as well. Then your extinction angle, it defines the angle at which mineral grains become optically extinct when viewed under a microscope. It helps to identify several mineral species and determine their orientation in thin sections. All these again properties requires individual discussion in individual, I can say, means it requires, this individual property requires individual lectures to understand. But just again, as we are not dealing solely into the optical properties of all the minerals, here we are just trying to look at the basic some understanding and some optical properties of the rock forming minerals. So we are kind of restricting our understanding here. So the next one, interference color, it occurs when polarized light passes through a mineral, that is after the insertion of your analyzer you will be able to see this kind of interference color. Again, that is based or that is a function of the retardation offered by the mineral. It depends on the mineral thickness, refractive index. Twinning occurs when two or more mineral crystals share a common crystallographic plane or axis, and it influences the physical properties as well as optical properties. And these are the again some other terms. Uniaxial, biaxial minerals relates to the number of optic axis in a mineral. So if there are one optic axis in a mineral, it is referred to as an your uniaxial mineral. If there are more than one optic axis, it is grouped under biaxial mineral. So again, it's an this thing requires an understanding or the relation between the crystallography or the crystal form of a particular or the crystal structure of a particular mineral. And 2V optic angle, this is again a property exhibited by biaxial minerals. Mainly it is simply the angle between the two optic axes in a biaxial mineral, but no, we are not going into details of that. Finally, to look at broadly some optical features of some different rock forming minerals, starting with quartz. So quartz has a very low relief, typically anhedral, colorless, and it is anisotropic. And again, like I was mentioning in the beginning, that quartz is used as a qualitative standard for assessing whether a thin section has been made correctly or there is some problems with in the making of the thin section. And it also shows some undulose extinction. Plagioclase feldspar, that is your series of rock forming and plagioclase minerals starting from albite to anorthite. This whole series, it also have a low relief and commonly occurs as euhedral, subhedral grains. It is also colorless, and sometimes you can see the cleavages. Many times you will be able to see one cleavage, sometimes you will be also able to see the other cleavage as well. It is also anisotropic. It displays a first order gray to white color, and often they are twinned, which are a property that is very common in plagioclase feldspar, polysynthetic twinning, when two minerals are sharing the same crystallographic structure. There are two minerals with individual symmetry in that, but they are combined or across a composition plane, they are related to one another, and that will add an extra symmetry in that particular set of mineral. So you can get polysynthetic twinning in case of your plagioclase feldspar. So twinning is visible in under microscope. Now all these photographs or this photomicrographs, because they are taken under the microscope. So this one is for plane polarized light when your one analyzer is involved. This second one is always the view of the cross polarized light after your analyzer has been inserted. Similarly, this is again for plagioclase. Similarly, for orthoclase feldspar, it has also very low refractive index because of its low relief, you can say so. It occurs as anhedral euhedral form. Sometimes it is often altered in nature to other minerals. It is also anisotropic, and you can also see a first order gray to white color, sometimes some common types of twinning as well. In case of olivine again, but it is now you can see the grain boundary are very well defined. So you can say the relief is very high. And they are generally equant, subhedral to anhedral. They are generally colorless, but also some coloring can be found depending on the presence of iron and magnesium, depending on their relative percentage of present. Obviously one set of the cleavage is present but is not very regular or imperfect. It is definitely anisotropic mineral, and it can give you second or even third order interference colors sometime. Extinction angle is usually 0. For muscovite and biotite, these are the two again mica minerals. So for muscovite and biotite, both have moderate relief. Both are generally means euhedral or subhedral in shape, sometimes tabular or flaky shape, you can say. In case of muscovite, it is colorless. In case of biotite, they are generally brown or greenish brown in color. Pleochroism is absent in muscovite, but pleochroism is present in case of biotite. You can simply rotate the stage and you will see that there is a variation in the color when you are rotating the stage. In both the cases, cleavage is basal cleavage is present. That means cleavage in one direction, and both are anisotropic with means generally again second to third order interference color. and also extinction angle, that is straight or 0 to 3 degree. That means the mineral is simply, again if I look at extinction, that the mineral is becoming dark or black when it is aligned parallel to the direction of the analyzer. That's your parallel or straight extinction. And when it is showing some color, that means it is not means becoming dark, means if it is becoming dark or black after a certain rotation with respect to the long axis that is kept parallel earlier to the direction of the analyzer. So in that case it will be considered under inclined extinction. But again, I am not going at this stage again to the details of extinction angle and what are the different ways to measure extinction angle, and in which case we will take the maximum extinction angle. The term extinction angle should be actually written as the maximum extinction angle, because we measure extinction from several grains, then we take the maximum value and then we assign it as the maximum extinction angle. So that is again a different point of discussion. For again pyroxene like augite, you will get high relief, and these are also anisotropic minerals, and you will be looking at two sets of cleavage, means well defined cleavage, almost orthogonal to one another. In case of hornblende, which is an amphibole, in that case you will be looking at cleavages which are almost at 120 degree or 60 degree to one another, and it has also very high relief, and also it shows very intense pleochroism. Again, it depends on the type of the amphibole, that whether it will show any pleochroism or not. So hornblende generally shows pleochroism, and obviously they are anisotropic. Hornblendes are also having an inclined extinction angle, and it ranges between 12 to 34, but mostly it is 23 degree. So, and finally calcite, which is not a silicate mineral, a carbonate one, but calcite is also a very common rock forming mineral. So for that, calcite has very low to low, generally sometimes high relief as well in some cases. That means variable relief it has, as well as variable absorption it happens when it is observed under plane polarized light, resulting to a phenomena referred to as the twinkling. It is simply like that of the stars twinkle at night. So the calcite grain will also come and vanish with a rotation of 360 degrees. So it is just like that. So color, it is generally colorless under plane polarized light, but in case of your cross polarized light, it will show very higher order interference color. And also it also possesses, calcite also possesses your polysynthetic twinning. So these are some of the properties that you will find in this kind of rock forming minerals. So I'll simply conclude my discussion, but remember this is just the preliminary what can be discussed within a single lecture within this series, that I have tried to accommodate several things, several terminologies which I couldn't discuss at this moment, can be discussed in detail in a you can say specific targeted course on optical mineralogy, because there is lot to discuss on optical mineralogy. Still, I would like to conclude my preliminary or the fundamental idea or the fundamental discussion on optical mineralogy. Thank you.